This is FRM Part 1, Book 2, Foundations of Risk Management, Chapter 5, Hypothesis Testing and Confidence Intervals. And this chapter could be called something like, if you remember anything from your undergraduate statistics class, it's probably contained in this chapter. Let's look at the learning objectives. Of course, we're going to worry about the sample mean and sample variance. We're going to work on some confidence intervals. And note, we have to calculate and interpret and construct and interpret. We need to worry about null and alternative hypotheses, whether it's a one or a two-tailed test, and then interpret the results of those tests. And then we'll go ahead and swing back to value at risk, which we've talked about in multiple previous chapters, and see how all the stat stuff relates to value at risk. Starting with the sample mean, there's a good definition. That first bullet point, sum of all the values in the sample of a population divided by the number of observations. Of course, you learned how to compute sample mean back in 3rd grade or 5th grade, whatever grade it is. But what's important for us inside of this chapter is not so much really the calculation of it, but to understand that we're going to use the sample mean to make inferences about the population mean. Remember, the population includes all of the data regarding a particular population, and it's very difficult to collect all that data inside of a population. And so to save time and energy and capital and all sorts of other stuff, we pick samples out of that population, and then we construct some tests on the samples. Central limit theorem, which we talked about in the previous chapter as well, provides a large sample approximate sampling distribution for the mean without having to worry about making any additional assumptions about the distribution of the population. Remember, sample mean is normally distributed with a mean of mu and a variance of sigma squared over n. Now, remember what I said about this population. So look at that first bullet point. The standard deviation of the population is almost always unknown. So we need to estimate the sample standard deviation so that we can kind of make some inferences about that. So there's a good formula for the standard error of the sample mean. And then we can quickly work through an example. We've got a mean of $15.50, standard deviation of 3.3. What is the standard error of the sample mean for a sample size of 30? And so let's just take that 3.3 divided by the square root of 30. So that gives us about 60% for the standard error. Sample variance. Now remember, square root of the variance is called the standard deviation. This is a measure of dispersion. So we have this distribution. So think about along the horizontal axis, we have all these observations, and they tend to cluster right in the middle. I talked about that back in the last chapter. And so the sample variance, what it does is it measures the dispersion from the mean. So the mean is kind of like the most likely outcome, not really statistically, but the ones that are around it, that's kind of the most likely set of outcomes. And then the further and further out you go, you're going to have a higher and higher variance. And remember that variance, and of course standard deviation, is a great measure of risk. And I think that's a great way of thinking about it. If you've got lots and lots of dispersion, or lots and lots of variability, or lots and lots of volatility, that must mean that you have lots of risk. And so there's a good formula for the sample variance. What we're going to do is sum from I equals 1 to n, and we're going to take the difference between each individual observation in the sample and the sample mean. And of course, we're going to divide by the degrees of freedom. I had a good explanation for you in the previous chapter about degrees of freedom, but essentially, we're trying not to underestimate. The sampling distribution of the sample variance when sampling from a normal population with a mean of mu and a variance of sigma squared is given to you in that formula there in the bottom blue box. How about confidence intervals? I love teaching my children and my students about confidence intervals, I always ask the question, what is something? I'll ask them about, what is your chance of winning a basketball game, or what is your chance of passing this exam or making a 90% on this exam? And they'll say, oh, I have a pretty good chance. And I'll say, well, give me a number. So they give me a number, and then I say, what's your percentile? How confident are you in that answer? Sometimes they say not very confident. Sometimes they say very confident. So what a confidence interval does is it gives us a range, a bottom number and a top number, under which we can be confident that a certain percent of all outcomes will fall within that interval. So if I ask my sons, what are they going to make on their German test, they might say, oh, we'll probably make a 90. And I'll say, well, what's the worst you can do? What's the best you can do? It's not really a confidence interval from a statistical standpoint, but it gives you the sense of what is reasonable for me as a parent to expect out of their performance on exams. So note in that first circle point I have, it is designed to contain the parameter's value within some stated probability, right? So my children could say to me, Dad, I'm 100% certain that I'm going to make between 0 and 100 on the exam. But that really doesn't do us any good, all right? So we need to have some kind of a confidence level. And most of the time, as you know from previous readings, researchers pick a 95% level of confidence when constructing confidence intervals. So look at that bottom bullet point, 95% of the realizations of such intervals. So if my children take the same test 100 times, 95 of them are going to fall within that range. And then 5% will not include that range. And so this is important for us to think about, especially as we end this chapter with value at risk, because we're worried about that bottom left tail of the distribution. Now, of course, we don't want to ignore the upper tail of the distribution. But do I really need to know that my son has a 2% chance of making a 20 on the exam? I mean, clearly, if they studied a little bit, you ought to be able to make at least 20, right? Maybe 30 or 40. I have this battle with them all the time. All right, so here's a good general formula for a confidence interval. We start with the point estimate, and that's probably going to be for confidence interval for the mean. That's probably going to be the sample mean. And then we're going to do a plus or minus, because we're going to add to go this way and we're going to subtract to go that way. We're going to multiply the standard error, which we just talked about a few minutes ago, by the reliability factor, which of course has everything to do with the level of competence. So think about this. If my sons say, I think I'm going to make an 85 on this German test, and they have a standard deviation of 2, and it's a 95% confidence interval, and they take this test 100 different times, then the reliability factor is probably going to be somewhere around 2. So I can do that. 2 times 2 is 2, so I can say 4. So the confidence interval here, just a general math, would be, what did I say, 85, add 4 and subtract 4. So 95% of the time, they're going to make between 81 and 89. Which, why are we talking about B's? Shouldn't my sons be making A's? All right, so let's continue some more conversation of confidence intervals. So there we go. Reliability factor can take the form of the Z or the T, and that depends, this is important, on whether or not the population variance is known or whether it's unknown. If the population has a normal distribution with a known variance, how often is that going to happen? But if it has a known variance, then you'll use the Z-score. And there's a good table at the bottom to look for confidence levels of 90, 95, and 99. And so notice what I said out there when I gave the example on the German test. There's that Z over on the right-hand column in the middle, 1.96. I said it's about 2. And so, just as kind of a professor over the years, I always just remember 2. I mean, of course, it's 1.96 to be more precise. And so look at that normal distribution picture up there. That's what we're doing. We've got that confidence interval is the lighter color there. And then outside of the confidence interval are the areas of, well, if we're doing 95%, then you got 2.5 out to the right and 2.5 way out to the left. Now, on the other hand, and this is probably more common than having the variance known, is if the population has a normal distribution with an unknown variance, then we're going to substitute the T-score in there for the Z-score. Now here's a good summary table for selecting the appropriate reliability factor. Remember, I mean, I think it's really safe to just try to remember that, 95%, it's going to be about 2. And that's, and this is what this table gives you guys, that's if the sample size is relatively large, greater than or equal to 30. If it's less than, then you have to make sure you're aware of whether or not the variance is known or unknown. So I would memorize this table pretty quickly, but I don't think that's too much of a challenge. How about an example? Let's suppose we sample 10 students, and these 10 students for the Part 1 FRM exam studied, and this is in terms of hours, right? Number of hours that these 10 students spent studying. So here we go. Calculate a 95% confidence interval for the mean time preparing for the exam. All right, so there's the sample mean and the sample standard deviation, 312 and 72. And by the way, you can do this really, really quickly on a financial calculator. If you have the HP, just hit your sigma plus sign, and then after you're done entering those 10 things, you just hit the mean and standard deviation. You get that. And if you have the Texas Instruments, you go into the data and enter those 10 as data, and then go into the stat function and hit your down arrow, and it gets you those. All right, so let's keep going here. Since the population variance is unknown, we must use the t. So we take the 312 plus or minus the 7.2 divided by the square root of 10 multiplied by that reliability factor, which is given to you in, boy, what a summary table that we have there at the bottom. But of course, when you look at this in the back of a textbook, or you look at this online, the t-table, it's way over there. It's a big full page. So make sure you can read it. Go down degrees of freedom. So in this case, it's 10 minus 1 is 9. And then run your finger over to, what am I running my finger over? Oh, to 2.5, because it's a 95% confidence interval. So this is a two-tailed test. So you throw 2.5 in either tail. Hypothesis testing. This is an assumptive statement about a problem, idea, or some other characteristic. It could be an opinion or a claim or a belief. The silly example that I give my students, both when I'm teaching an investments class or a derivative securities class, or whether they're MBA students or not, I look outside and I say, I'm looking at the grasses out there, and the grass needs to be cut, but I believe that the average length of the blade of grass out there is 2.5 inches long. And I ask my students to go out and say, what do you think that is? And students, they'll look at me and they say, Jim, we don't care about the blades of grass. But I say, go ahead, play along. And they'll say, okay, 3. Well, what's the population? All right, so we're arguing here. And this is what the hypothesis test does. It's really an argument. It's an opinion. One person says something, another person says another thing. And so rather than, kind of duke it out, we say, well, let's perform an hypothesis test. So what we have to do is we got to go out and say, okay, what are the length of the blades of grass throughout the world? Oh my gosh, who can do that? So maybe we'll just limit it to blades of grass on our campus, or blades of grass back where the sun shines in the afternoon, or however you want to do it. So this really hypothesis testing is a battle between what I think the length is and maybe what somebody else thinks the length is, or what maybe the college landscaping service says, the average length of the blade of grass is 3.1 inches. And I'm looking out there and I'm thinking, there's no way it's 3.1 inches. Now, of course, blades of grass, that's silly. Let's look at a better example here. The mean return of small cap stocks is higher than that of large cap stocks. So what do we need to do? Collect and examine a representative sample to determine if the hypothesis is true. So here are the steps. So state the hypothesis, which we did right there, right? Mean return of small cap stocks. All right. Select the appropriate test statistics. So then we've got to go back here. Let me just go back one more. We have to go back to whether or not we know stuff, whether or not we have more than 30, right? where am I here? Specify level of significance, state the decision rule, whether we're going to accept or reject the null hypothesis, and then sample statistic, and then make the decision. All right, so this is how we set up the null hypothesis. It's denoted as H sub 0 and represents the current state of knowledge about the population parameter that's the subject of the test. So typical statements include that mu equals mu sub 0 in the hypothesis, whatever that hypothesis might be, or greater than or less than or equal to. And then the alternative hypothesis is the alternative, which is denoted as H1, although back in my graduate school days, we always did H sub A as the alternative, but who cares what the subscript is? Just know it's what the conclusion will be if there is sufficient evidence to reject the null. One- and two-tailed tests, this ought to be relatively straightforward. You know, we have this normal distribution. What are we worried about? Are we worried about just the left-hand side? Are we worried about just the right-hand side? Well, in that case, then it'll be a one-tailed test. Think of it this way. What we're doing is shoving all of that confidence level. We're shoving all of the 5%, if we have a 95% confidence. We're shoving all of that 5% even into either the left tail or the right tail. But many times we want to chop it. So we're going to put half in each tail. So that's the difference between one and two-tailed tests. All right, a test statistic is a quantity calculated based on the sample whose value is the basis for deciding whether or not to accept or reject the null hypothesis. So the test statistic there is going to be a good formula. It's going to be the sample stat minus the hypothesized stat, or the hypothesized value, divided by that standard error that we talked about earlier. We can do this with a z, we can do it with a t, we can also do it with the chi-square if all of our values are positive and if we don't have a normal distribution. So we're going to divide the set of values into the rejection region, which we call critical, or the non-rejection region. Remember that non-rejection region is consistent with the null hypothesis. How about type 1 and type 2 errors? These are known as statistical errors. A type 1 error occurs when the true null hypothesis is rejected. So let's suppose that we believe that the mean is going to be, mu is going to be 0 when mu is in fact equal to 0, and we reject that. And so what we're trying to do here is we're saying that the null hypothesis turns out to be true, but we don't believe our eyes. We don't believe the results. That's just a type 1 error. Type 2 is failure to reject a false null hypothesis. So type 1 and type 2, they're kind of opposites, they're kind of reciprocals, but not mathematically so. That level of significance, alpha, represents the probability of making a type 1 error. So what's the decision rule? It is the procedure followed by analysts when deciding whether or to reject or to accept the null hypothesis. So make sure you use the phrase "not to reject," because stats professors go mad over this. You don't say that you accept the null hypothesis. We can only gather sufficient evidence to support it. It's kind of like that. That ruling that came down in the NFL. You guys know I like to give sports analogies. Do you remember the whole Deflategate with Tom Brady? Where he was letting air out of the footballs before one of their cold playoff games, or maybe it wasn't even a playoff game. And the NFL ruled that there was not sufficient evidence to prove that Tom Brady knowingly or purposely, whatever it was. So remember, we say not to reject. And of course, prior to the decision, we need to decide whether we're going to do one or two-tailed test. All right, so here are the three cases. Let's suppose that we have a one-tailed test and we're concerned about the left. So we're concerned about everything down on the bottom left. So the decision rule is to reject the null hypothesis if the test statistic is less than the critical value. Otherwise, do not reject the null hypothesis. And then, of course, just the opposite holds true for the one-tailed test over on the right. If the test statistic is greater than the critical value, then we reject the null hypothesis. And then the two-tailed test is to reject the null hypothesis if the test statistic is greater than the upper critical value or less than the lower critical value. All right, how about hypothesis tests concerning the mean when the variance is known? All right, so here there's our null hypothesis when the variance is known. So we're going to use the Z statistic. We're going to compare that to a critical value. And since we're doing a 95% level of confidence, we're going to use that 1.96. Remember, I said that's kind of close to 0, so plus or minus 1.96. So our decision rule is to reject the null hypothesis if the Z statistics falls within that critical region. Scenario 2, when the variance is unknown, we've got to use the T-test. So instead of, I mean, look at that formula there. Boy, don't they look pretty much the same? Except for, what are we doing? We're substituting the sample variance in there in the denominator. And we've got to worry about degrees of freedom here as well. So look at the decision rule at the bottom. Reject the null hypothesis if the test statistic falls within the critical region. And then the Chisquare test is typically used to establish whether a hypothesized value of the variance is either equal to or greater than or less than the true population variance. So the Chisquare, we're testing whether or not what we pull out of the sample is the same number as what the true population is. And so there's the null hypothesis that the sample is equal to the population variance, and then there's the formula for the Chisquare statistic. Notice in the numerator you have the sample variance in the numerator, and then there's the n-1 degrees of freedom. How about an Ftest? This is used when you have two independent random samples from the same population. Let's call them n1 and n2, and they have two sample variances, of course, S1 squared and S2 squared. And so what we want to do is see if those two things are the same. If we pull 2 out, are they identical to each other? Remember back here with the Chisquare, we're pulling a variance out and think, is it the same as the population variance? Here, we're pulling out 2 sample variances and seeing if they look alike. We see if they're the same number. And there's the F. You just put the 1 in the numerator and 1 in the denominator. And you got to worry about the degrees of freedom for each one, because, you may only be able to get, 52 out of this sample, and you might be able to get 93 out of that sample. So you need to make the adjustment there. Now, how about backtesting value at risk? Remember what we talked about in the prior chapters, is that the value at risk measures the minimum loss that a portfolio or any other kind of variable, the minimum loss that will occur just 5% of the time. What we want to do is we want to use these sample means and sample standard deviations and confidence intervals and confidence levels. We want to do this to backtest the value at risk to ensure that the model is forecasting losses that are within the forecasted frequency limits. So exceedance is said to occur when the value at risk measure is exceeded during a given testing period. I mean, let's just do the obvious one. Let's suppose we have a 95% confidence and we calculate a value at risk of, let's just say, $1 million. And over the next 100 trading days or 100 trading weeks or 100 trading years, whatever our sample period is, that 40 of those outcomes exceed our value at risk. Well, what we have to do is conclude that, boy, that model pretty much stinks, right? So we want to make sure that it's 5%, right? We pick 5%, and we want to make sure that it's 5%. And so here's a little chart about back testing and how the model may be underestimating the risk or overestimating the risk. And this is just can be determined by the number of exceedances greater than expected or less than expected. And that should make perfect sense. Let's do a quick example here. 10 million value at risk of a portfolio. There's a 200 trading day period. Daily losses happen to exceed 10 million 18 times. Is the model effective? All right, so with a 95% confidence interval, we expect to have exceptions 5%, no more than 5% of the time, right? So that's, what's 5 times 200? That's 10, right? So, boy, what do we have? 18. So 18 is greater than 10. So we've got these exceedances. So it occurred, exceptions occurred 18% of the time. So the model is underestimating risk. What that means then is we need, as good financial risk managers, go back and decide what the heck's wrong with our value at risk model. Maybe we were using the historical model and relying on too long of a time window, and maybe we need to do something else. Hey, that takes us right through chapter 5. That was fun. Next up, linear regression with one regressor.